This is Core Pure Maths paper 2 from 2022. Let's just do this. So the mistakes, well, there's a 3 here and a 3 here, but this is a minus 3, so that should be tan inverse of minus 3 over 3. And then on line number 3, when you're dividing two complex numbers, the arguments subtract, they don't divide. So this should be argz1 minus argz2. And then, of course, to correct their work, tan inverse of minus 1, which is what this would become, is minus pi over 4. And then we're going to take away, as we've said, so it's going to be minus pi over 4 minus pi over 6, which is going to make minus 5 pi over 12. Question number 2, we'll call the people enrolled in construction, or the number of people enrolled in construction, C, and then D and then H, respectively. C plus D plus H is this number. C equals H plus 370, I think is what that says. And then here, decimal multipliers, this will be 1.0125 times C to get this, and then this one is 1.025, and this one is decreased, so it's 0.98. Add those all together, you get 1,110 as before, times 1.0027, which is the decimal multiplier for this, I believe. Divide by 1,000, then yeah, sure, it's 100 and so, yeah, okay. So we just put this in a matrix, right? This needs rearranging. It's going to be C minus H equals 370. And then, of course, you've got no D's in that row there. And then we just put all the rest of the numbers in. We get this times this is roughly this. And your calculator can do this, because your calculator can just work out the inverse of this matrix for you. And then you can do that times by this, because you can just front multiply both of these sides by the inverse matrix. Just to put the inverse matrix over here, just type that in the calculator. I haven't even bothered to work out what the inverse matrix is. You get these numbers. And then maybe just write a line just being very clear and saying this. That should be a 350 if that's a 350. Or maybe that should be a 250 if that's a 250. I don't know. Check the mark scheme or type it in a calculator. One of those is a typo, and I'm not sure which. Next one is question number 3. Induction then, so let's just check it for n equals 1, which is just m to the power 1. Well, this is what they give us. This is 2 times a over 2 is just a. This is just a 3, so yeah, that works, that checks out. So now we're going to assume that works for n equals k. We need to just write these things down. So we're going to assume m to the k is equal to that, with some k's in there. And now we're going to consider m to the k plus 1, which we can just write as m to the k times m. This is a standard trick for matrices and induction proofs. So that's going to be by the induction step, or the assumption step, sorry I should say, that's going to be that there. And then m is just that. We're going to multiply these two things together. This times this is 3 to the k plus 1, plus this times this, which is 0, so that just doesn't do anything. And then we're going to have this times this, and then this times this, which gives us this complicated bit. And this times this times this is 0. And this times this times is 1, so that's fine. Now we just need to sort this out until we get the thing that we want. So okay, well, if you expand this out, you get minus a half a over there, which is that bit, and then this is one of these plus a half of them. So that's going to be 3 over 2 of them. We can put that 3 into there, I think, to make a 3k plus 1. And that leaves an a over 2 behind, which we can then factorize out. And I think this is exactly of the form this, with some k plus 1s here, so I think it's true for n equals k plus 1. And then we write this thing. There's some bolded figures in the exams, in the mark scheme, which are the bits that you have to say. So I tried to say those, I think. Anyway, triangle T has vertices this. It's transformed by this, and this happens. So the area scale factor of a transformation is the determinant of the matrix that you've used. So the scale factor from here to here is 243. Which means the determinant of m to the n is 243. So, but of course the determinant of this is just this times this, which is 3 to the n minus nothing. So we get 3 to the n is 243, which means n is 5. So we've got that bit first quite quickly. And then we can just get this point to go there by doing this. So we put 5 into here, and then we just shove this point next to it, and we're aiming for this point. The denominator, sorry, not the denominators, but the bottom half, notice, just immediately works. That's fine. So then we just do 2 times this bit, and then minus 2 times this bit equals 1, 2, 3. And I mean, there's just, yeah, I don't know what you're getting 5 marks for here, but that's the answer. And we'll go on to question part 4. I did this question like an absolute madman just because I was bored. You need to, I mean, the best way of doing this is just to turn these into numbers of the form a plus bi, and then just add them together and then turn them back again. I decided to draw it. So this is Z1, this is Z2. Notice how the angle is like quite close to 180 or pi or whatever. So Z1, Z2, Z1 plus Z2 is this way. And what I said was this angle here is pi over 3. That's the argument of this first one. This angle there is pi over 6 from this line across. This angle here is pi over 6. Which means if I continue this dotted line a bit further, this angle here is pi over 6, because it's pi minus this one. And this angle here is just alternate, so this angle here is pi over 3, and that should point at this angle here, sorry. But of course that means this angle here is just pi over 6 plus pi over 3, which I believe makes pi over 4, which is really nice. Does it make pi over 4? We get 3 plus 6 is 9, divided by 18. Sorry, it makes pi over 2. Pi over 2, which is 90 degrees, which is a right angle, which is really great, because that means if I have the length of this one, which I do, it's 6, and the length of this one, which is 6 root 3, I can just do Pythagoras to work out the length of this one, and hope that equals 12, and wouldn't you know, it does. That's cool. And now what about the argument bit? Well, that's going to be this angle here. There's a few ways you could do this, but this is a right angle triangle, so we can just do tan inverse of this length over this length, which is 6 root 3 over 6. So tan inverse of 6 root 3 over root 6, plus this pi over 3, sorry, because this whole thing there is the argument of this Z1 plus Z2. So pi over 3 plus that result there. 6 is cancel. Tan inverse of root 3 is, I believe, what, pi over 3 again. So you get 2 pi over 3, which is what they wanted us to get, and we have that shown. Good. So probably just do it in a different way to that because it's much easier. Now, the thing like this here is a half line starting at the point 5 with argument that's, and this is like, it's 120 degrees, isn't it, for people who still work in that figure, so it's over this way somewhere, starting at 5. And we want to know the least value, so z can take any position on this line here. We want to know the least value of the modulus of z. Now, that's the distance from the origin to it. So, of course, the least one will be the one where you go to a right angle to that point there. So this here will be the value of z for which the mod of z is the least. But we can just turn this into sort of Cartesian equation line stuff, right? If the argument here is 2 pi over 3, that means the gradient of this line is tan of 2 pi over 3, which is just minus root 3, because tan is opposite over adjacent, which is the same as rise over run when you set up a little triangle, so therefore tan of an angle is the same as the gradient. You can use that trick. So this line is just y equals minus root 3x plus c. Put in the point 0, 5, and you very quickly get that c is 5 root 3. And then this line here it's perpendicular, right? So its gradient is 1 over root 3, and it goes through the origin. So that's quite easy. You put this equal to that, and you times everything by root 3, because obviously you do, and then you just rearrange that for that. And then you can put that back into here to get that. And you want to know the distance from you know, you want to know this distance here. You have this point as this. So you just do a bit of Pythagoras on these 2 points, and you type it into a calculator, and you get that back. Question number 5 then is quite a nice one. I mean, every single person will have been shown this in lesson time. You do sine of both sides, you do implicit differentiation, which is cos y dy by dx here. X differentiates to 1. Divide by that. Cos y is the square root of 1 minus sine squared y. And you have what they wanted you to get, because of course sine y is x, so sine squared is x squared, and you put that in, and you have this. Now you're being asked to show this thing here. So let's just do it again, but with an e to the x here. So let's define y to be that, put the sign on the other side, differentiate implicitly, we get this, we divide, we put the same thing back in, we get this. And we want that to be 0 for stationary points. Now, of course, this denominator doesn't matter because you could just times both sides by it and you get e to the x equals 0. But that doesn't have any, that's never 0, it's always positive. So there's no stationary points, and that's done. Question number 6 then is kind of cool. We're given this is one of those questions about roots. We know that, you know, this one here is alpha, beta, gamma. It's actually negative q, because you've got 3 of them in that case. But I think what we first need to do is get rid of this 4, because otherwise none of our stuff works. Let's divide by 4 first, we get this. And now we can do some stuff. The first thing they're asking about is p. Now this one is going to be just the sum of the roots, so alpha plus beta plus gamma, and it's going to equal minus p over 4, because these are singular roots, so they're all negatives. And we get this, and then of course what we could do is we could square both sides of this, but first we probably want to use this. This one is the sum of the pairs of them, so alpha beta plus beta gamma plus alpha gamma, and that just equals the what it does, the negative here, because they're in pairs. Now if I square everything here, the negative obviously goes away, and you expand this out, you get that, which is probably just a result that you know because you've seen it a lot before. You can shove this result into here, and you can shove this result here into there, and you get this. And then you can times by 16, and you get p and square roots, and you get p is 12. So that's that done. Given this, determine the value of q. So like I said, q over 4 is, or minus q over 4 actually, is alpha, beta, gamma. So how are we going to get this out? Well, let's consider this for a second. We know that's equal to 14 over 3, but we can also just combine it into one fraction by timesing this by beta gamma, timesing this by alpha gamma, timesing this by alpha beta, and then putting them all together you get this. But we know this is minus q over 4, we know this is minus 7 over 2, we know together they make 14 over 3. Cancel the negatives, do some stuff, and you get this, q is clearly 3. And without solving the equation, do this. So, I mean, we have these with the results. I put the q and the p into these to get some actual numbers. When you expand this out, you're going to get alpha beta gamma, which is cool because I have that result. And then you're going to get an alpha beta and a minus 1, so that's minus alpha beta. But you're also going to get a minus beta gamma and also a minus alpha gamma. So that's cool. That I can just write as that. And you're also going to get a alpha times minus 1 is plus alpha. Beta times minus 1 is plus beta. And gamma times minus 1 is plus gamma, and then there's just the minus 1 at the very end. But I have all of these results, they're all there, so I'll put those all together and I'll have my final answer. Cool. Question number 7. You've got a tangent perpendicular to the initial line, which is dx by d theta equals 0. Of course, x is r cos theta in polar coordinate land, but r is 1 plus tan theta. So let's find out dx by d theta. By differentiating this, you can use some product rule. This differentiates to sec squared, leave that alone, this differentiates to minus sine. You can set that to be 0, I guess first. Sec squared times cos is just sec. Set that to 0. This is not the most obvious thing ever to solve. It takes a bit of playing around. I wrote it all like this. I expanded this out, and also tan is sine over cos, so that makes sine squared over cos. But now you can put these two fractions together because they've got the same denominator, and you get this, and that's just cos squared, I believe. At least it is if you're in this range. Yeah, it is just cos squared. Divide by cos is just cos, and then you can add sine. You can divide by cos. You get this. You can solve that. You get this again in this range, and then of course you can put that into there. 1 plus tan pi over 4 is 1 plus 1, which is 2, and we'll have our answer here that we wanted. Good. And now we're going to find r. So let's integrate the curve. Let's do the half integral of r squared idea, where we're going to integrate between the initial line of just theta is 0 and the line theta is pi over 4, getting us to over there. This should have really started over there, but it doesn't really matter. So we're going to integrate between those two lines. Of course, now that finds the area of the curve trapped between the lines, which is actually this white area here. So my plan is to do that integration, so this integration here, and then when I have my answer, I'm going to work out the area of this triangle, and I'm going to take away this white area, and I'm going to get r. So let's do this integration first. We expand out. This I can integrate. This I think I can integrate, right? Because it's in the formula book. It's just log sec. And this, we just need to know the trick here. You can write tan squared as sec squared minus 1, I believe. And actually the 1's cancel here, which is super kind of them. And then that's in the formula book. That obviously integrates to tan, because everyone knows tan differentiates to sec squared. And then we put in pi over 4, we put in 0, and we just do some maths, and we eventually end up with this. And there, like I said, now I need the area of the triangle. Now, how do I go about doing that? Well, I know that distance there is 2, because that's the r value at pi over 4. So that's cool, I know that. And then what I decided to do was look for this length here. So if y is r sine theta, r is of course this, then just put theta is pi over 4 into there. You get 1 plus 1 times 1, which is just... no, you don't. Yeah, you do. No, you don't. You get 1 plus 1, and then sine of pi over 4 is root 2 over 2, isn't it? So 1 plus 1 is 2 times root 2 over 2 is just root 2. So that distance there is root 2. It's the y-coordinate. And then you can do some Pythagoras here. 2 squared is 4, minus root 2 squared is 2, so that makes 2, rooted is root 2. And then we can do the area of this triangle as a half times root 2 times root 2. But that's just 1, I think. So now we can just do 1 minus this thing here. And 1 minus half is a half. And then we can factorize out the half, and I think we end up with the answer that they wanted us to get. Question number 8 then is quite possibly the easiest vectors question I've ever seen in my life. All we need to know here is the dot product, and we just need to do the dot product with these two vectors here. So this dot this is equal to the modulus of this times the modulus of that times cos theta. Now that's not actually in the formula book, but the cross product is in the formula book, and that is sine. So if you just remember that the dot product is the other one, it's cos, then that's pretty straightforward. Of course, we dot these together, you end up just with a here. This is 4 plus a squared, this is root 2, this is minus a half, so you do all that. You square both sides here to get this, and now you do some stuff and you get this. Now, only one of these answers is correct, and it says determine the value of a. So which one is it? Well, you go back up to here and you realize, well, that's positive, that's positive, that's positive, and there's a negative in front, so A must be negative for this here to make any sense, so A is -2 is the only correct solution here. Verify according to the model that there is a common point here, so I mean all we have to do, I've put A into here I guess, all we have to do is write the x, the y and the z line out here, so that's that, and we want those to be equal to the x, y and z line from here, so I mean this is just 4 here, so -1 plus 2 lambda equals 4 if these are going to have a point of intersection, and 5 minus 2 lambda equals -1 plus mu, and so on. So we get those three. Of course, this is we just solve immediately, this we just solve immediately, and then you want to check that those two solutions make this y-coordinate also make sense, and it turns out they do, which is good. So they meet at the point, well, 4, because this one's always at 4, 2, because this one's at, sorry, 4 something, 2, because this one's always at 2, and then if mu is 1, this just makes 0, which we already found out, so they meet at the point 4, 0, 2. And they definitely meet because it's all consistent, and that's the point they meet at. Their position is modeled as being a common point, which is this point here, and we've got a plane which is modeling the ground. What's the shortest distance from the point to the plane? Well, this is just a formula in the book. We have the plane in this form, which is good. We have a point, so let's just shove those values into there. We get this, and then we get this, and that will be the distance. And by considering model, comment on your answer. Well, is the ground going to be completely flat? If it's not, that will cause some problems, I guess. I don't know, something. It's 1 mark. Move on. Question number 9. Quite an interesting question. It's unusual for question number 9 to not be worth that much. It's the last question. We differentiate this, of course. You can write it like this to make chain rule maybe easier for you. Bring the n down, take 1 away, and then times by the derivative of cosh, which is change. So we get this. That's the first derivative. Do it again. This is going to make a product, I guess. Bring this down, take it down to an n-2. Then you have another derivative of this, which makes that a sine squared, and then instead, because we've done that one and left this one alone, we're going to leave this one alone and differentiate that one for a cosh, which is nice because that bumps that buck up to an n. You can also write sine squared, this is in the formula book, as cosh squared -1, so that's just in the formula book there. And then you could do a bunch of expanding here. So I think I expanded out these two first, and along with those two, and now I'm going to do a quadratic expansion kind of thing here, and we eventually end up with all of this. This, thank God, cancels with that. We end up with this, which I think you can just about squeeze into here and get the correct answer. I hope it does look right from here, so that's nice. Yeah, that looks good. So we're done. Determine this. Now, I did this in a stupid way, or maybe I didn't. Maybe I did it in a really smart way. Who knows? It's almost certainly the best idea just to differentiate this and then differentiate it again in a normal way. I just said that this is all it is you just derive this twice more. So then replace this with this. But like, this is just something minus something else. So when you do derivatives, you can just derive this one and this one separately. So that's what I said here. But by this idea here, I mean the n squared and the n minus 1, they don't matter. They've got nothing to do with the derivative. So you can bring those out. But like the second derivative of this, you've just learnt is this. So you just shove that into there. And the second derivative of this is this with n minus 2's in positions for all of the n's. So we end up with that there. And yeah, I thought I was being really smart when I did that. And that is a completely correct answer. The problem is the next bit, which talks about Maclaurin series. Now, Maclaurin series are in the formula book. All Maclaurin series are, by the way, and I will always say this every time they come up, is they're just a Taylor series evaluated at x equals 0. Literally, that's all that is. So what we're being asked to do here is find f0, f dash 0, f dash 0, and so on until we get 3 non-zero ones. So okay, well we'll just call f of x this. Cosh of x, f dashed we learnt on the previous slide was this. Cosh of x is defined to be this. So cosh of 0 is going to be 1 plus 1 over 2, which is just 1. So basically, when we have coshes only, we'll just get 1s, and that'll be fine. That'll be non-zero. But when we have a shines in here, that's going to be 0, because shine is the same, but with a minus. So it'll be 1 minus 1, which is 0, so that will be 0, and that will all go away when you evaluate at 0. So f dashed of x won't help us, but f dash dash will, because that only has coshes in again. So okay, f0 is 1, f dash is 0, f dash dash, when we put 0 into here, as the x's, we get a 1 here, which gives us n squared, we get a 1 there, which gives us this, expand that out when we get this, I believe. That should totally be, yeah, no, sorry, that's correct, good. So that we get that. Now, f dash dash dash, I'm just going to assume has a shine in it. And I'm assuming, I think that's a completely fine assumption to make for a couple of reasons. One, because they made us work out this, so clearly this is going to be the next term that matters. And two, I mean, it's obvious that when you take this and differentiate, you're going to get a shine term on you, so that's fine. So okay, let's look at this, and let's sub in x is 0 into it. Now, I have no idea why this is only worth 2 marks, because you have to do it in simplest form, which means... so all I've done here is I've made all these coches 1, and then I've just written out the rest of the ends, which is not fun. But anyway, now we have to expand everything so we can cancel a load of stuff out. And stuff does cancel out, to be fair. It does. It just took ages, and you had to be really careful. You eventually get this. So now we're set. We're good to go. So we have all of this. These are our first 1, 2, 3 non-zero terms. We shove them into here. We put the x squared over stuff, and that'll be that. Yeah, that's the whole paper. Thank you for watching, and I'll see you next time.